This video, we're looking at the factors that affect resolution and ultimately exploring three of these factors as the wavelength of the wave that is used in the microscope, the limit of resolution, and the numerical aperture. But for purposes of revision, it's important to reflect on the fact that in microscopy, if we're talking about resolution, we're looking at the ability of a microscope to resolve new details or bring new details into focus. And we are ultimately expressing this in terms of the resolving power of that microscope. Now, there are a number of factors, a number of things that affects the extent to which a microscope is able to resolve details, or to say factors that go on to affect the resolving power of that microscope. And the first of these considerations is the wavelength of the wave that is being used. And so whether electron microscope or light microscope, we are considering the wave-like aspect of them. And in the instance of a light microscope, notice that light is considered to be both a particle and a wave at the same time. That's what we call the wave-particle duality of light. And owing to the fact that we can consider light as a wave, then we can consider the wavelength of that light that is used in the microscope. The general notation is to say that wavelength is inversely proportional to the resolving power or resolution of a microscope. How is this able to play out? This fundamentally means that if you have any optical instrument that is using light, the wavelength that you use, the shorter the wavelength of that light or particle, whether it's an electron in an electron microscope or it's light in a light microscope, the wavelength of that medium is inversely proportional to the resolving power or the resolution that you are forming. That is to say that the shorter the wavelength, the higher the resolution, and vice versa. That also fundamentally means that the longer the wavelength, then the smaller the value of the resolving power in that particular extent. A way to visualize this is to look at the equation E equals hc over lambda. If you look at that equation E equals hc over lambda, where E is the energy of the wave and h is the Planck's constant and c is the speed of light in vacuum, and lambda represents the wavelength. You recognize that from that formula E equals hc over lambda, the shorter the wavelength, the lower, the higher the energy, because the wavelength is a denominator. Whenever the wavelength is small, the value for E, which is the energy of the light wave, is higher. And whenever the wavelength is bigger, then the value for E is smaller in that particular regard. Now, in light microscope, we consider the work done and the efficiency of the light in terms of its ability to resolve details. And notice that there is a work-energy relationship. And that work-energy relationship can be able to allow us to estimate how much work is done in a system, or how much energy we've used based on the amount of work done. So, work-energy relationship. If we have a certain value of energy, that corresponds to a certain amount of work. And so E equals W in that particular regard. If you have this idea, you recognize that in a light microscope, the amount of energy that is carried by the light rays is equivalent to the kind of work that you're supposed to do or perform with that light energy. Now, how do we measure or visualize the efficiency of that light energy in a microscope? We can't measure that work output unless we look at it in terms of the ability of that light to resolve details or bring new details in focus. And so in microscope, a way of estimating the efficiency of the light wave or the work that is done is to measure the resolving power. And so that is to say that if you have light of higher energy, those are going to be more efficient and resolve more details. And so the higher the energy of the light waves that we're using, the higher the value of resolution that we are getting. Thinking about the earlier statement that I made, that the shorter the wavelength, the bigger the value for E, using the formula E equals hc over lambda. Whenever wavelength decreases, the value for E, which is the energy, increases. So that is to say that whenever we have light of shorter wavelengths, those particular light rays have a higher energy, and that higher energy would enable them to perform better work output, and that work output is seen in terms of the ability of that light ray to resolve details, and so resolution is going to be high. In an instance where these lights have longer wavelengths, what is going to happen is that the value for E is going to be lower. It means that these light rays, owing to the fact they have longer wavelengths, are going to have very little energy, and that little energy is less efficient in producing work output, and so we have less resolution in that particular regard. So this is a way to visualize how wavelength is ultimately able to impact on resolution in a microscope. Another factor that affects resolution in a microscope, apart from wavelength of the light, is the limit of resolution of that microscope. And notice that the limit of resolution ultimately expresses the shortest distance of separation that can exist between two entities, for which it will be permissible to see those two entities as distinct. You realize that whenever you keep bringing two things closer, you continue to see them distinct until you bring them so close. And when they get so close, it gets to a point in time where you don't see them as separate anymore. If those two entities are so tiny and they are so close, then it's even much more difficult to distinguish them as separate. So when we're talking about limit of resolution, we are looking at what will be the smallest distance of separation for which we would still be able to see those two things as separate. That is to say that going below that distance of separation, it will not be possible to see those two entities as separate or distinct anymore. So for example, your eye as an optical instrument, the human eye as an optical instrument, has a limit of resolution of 0.01 millimeters. That means that any two substances, any two entities that are separated by 0.01 millimeters can be able to be detected by the human eye as distinctly separated. But if the distance goes below 0.01 millimeters, then it will be impossible to visualize those two entities as two different things. Now, owing to this, if the limit of resolution of a certain microscope is so tiny such that it allows us to be able to see some entities that are separated with the tiniest distances of separation, then that must be a powerful microscope. That must be a microscope with a high potential of resolving and bringing new details into focus. And so generally, the smaller the value for limit of resolution, the higher the resolution of that microscope. So a microscope that has a limit of resolution of say 0.1 micrometers will be better than that one that has a resolution of 0.1 millimeters, because 0.1 micrometers is smaller than 0.1 millimeters. In that same vein, a microscope that has a resolution of 0.1 nanometers that has a limit of resolution of 0.1 nanometers will be better than the one that has a limit of resolution of 0.1 micrometers. And so the smaller the value of limit of resolution of that microscope, then the better or the higher the resolving power of that microscope. And so that's how limit of resolution impacts on the extent of resolution within a microscope. The next factor that affects resolution in a microscope is the numerical aperture. And numerical aperture is often expressing the light capturing ability of that objective lens. And so if you look at objective lenses of microscope, by design, light rays move through the condenser lens of the microscope, then pass through the specimen and carry the specimen details. Now the specimen details that are carried by those light rays are now able to enter the objective lens, which collects some amount of that light carrying the specimen details. And that is what ends up in the eyepiece lens in the image that is finally formed. That is ultimately saying that if the objective lens is not able to capture as much light ray carrying the specimen details, then you're going to lose some level of details. Then resolution is going to be affected in a way. And so you have two different objective lenses. One of them is able to capture a lot of light rays as compared to the other. Then the one that captures more light rays is going to have a better resolution ultimately than the one that is able to capture less. And so given that numerical aperture refers to the light capturing ability of the objective lens, then numerical aperture can be a way to estimate the extent of resolution or resolving power that you can have. And so the general rule is this: the higher the numerical aperture, the higher the value of resolution, and that is to say the better resolving power of that particular microscope. And the vice versa is true. The opposite is true in the case that the smaller the value for numerical aperture, then the little the extent of resolution in that particular regard. Thank you for watching this video, and I urge you to subscribe to this channel and share this video to your friends. Thank you. And in another tutorial, we would consider some other things related to microscopy. Thank you for watching.